Hi everybody. In the last lecture, we talked about what happens to a 1D solid when we go from a continuum description to a discrete description. What do we mean by that? When we treat this solid as a continuum, meaning we completely disregard the existence of atoms, that the solid is composed of atoms, we get a relationship between frequency and wave number, omega and q, that was linear. The slope of this relationship was basically the speed of sound or the speed of elastic waves in the solid. When we now replace this continuum picture with a discrete picture, meaning we now don't disregard the presence of atoms, we put the atoms in, we consider our solid, our 1D solid, to be made up of atoms with the interatomic distance A. This relationship between omega and q ceases to be linear for all values of q. It is still linear for small values of q, but for large enough values of q, the wave number, the linear relationship ceases to exist. So here is what I mean. Let's look into this a little deeper with this using this picture. So here is the omega versus q diagram. The dashed line basically represents our continuum result, and the solid red line displays the discrete picture, meaning when we replace the continuum solid with a solid composed of atoms. And of course, when we go to the discrete solid, a solid made up of atoms, we also see other interesting features. For example, this omega versus q curve displays periodicities. In fact, the omega versus q line is periodic with the periodic length 2 pi over a, where a is the lattice parameter of this 1D lattice. Right? So the unique part of the omega versus q behavior is really contained within a q distance of 0 to 2 pi over a, or minus pi over a to plus pi over a. So that was the story so far. So now we are going to ask the question as to what will happen if we still stick with the 1D lattice, but we have more than one atom per lattice point, per basis. Bear in mind that the picture that you're seeing right now applies to a 1D lattice where we have one atom per lattice point, per basis, right? So now we are going to alter that crystal and put two atoms per lattice point, and we are going to see if that is going to change our picture of omega versus q. In fact, what we will see is that it does add a interesting new feature to this omega versus q diagram. Before we jump into our lattice that's going to contain two atoms per basis, let's continue to remember that the q values that are allowed are going to be spaced by 2 pi over L, where L is this length of our 1D rod, which is a macroscopic quantity. So when L is large, 2 pi over L will go to 0, and so the q axis is a continuum in that sense. However, we want to bear in mind that the various values of q is just labeling the different modes of vibration. So essentially, we have several patterns of vibration, each one in this 1D case with a different wavelength. And so the q values are merely helping us with the bookkeeping. They are just labeling the different patterns or modes of vibration. Okay, so with that in mind, we are now going to move on to our lattice, 1D lattice with two atoms per basis. Okay, so here is our new 1D lattice. Let us be careful and make some important observations. There are two types of atoms, right? There is the red atom and then there is the black atom. So there are two types of atoms per lattice point. we're going to assume that the atoms are all spaced by distances a. So the distance between a black atom and a red atom is a, and the distance between that red atom and the next black atom is also a. So bear in mind that now our lattice parameter is 2a, right? So 2a is really the periodic distance of this 1D lattice in real space. And we are going to call the mass of the red atom as m1 and the mass of the black atom as m2. And we are going to label the atoms as before, n minus 1, n plus 1. And because we have two atoms, I'm just going all the way to 2n plus 1, and the atom before the 2nth atom is 2n minus 1. So we are labeling the atoms just as before, and the masses of the two atoms are m1 and m2. The lattice parameter is 2a, with the interatomic distance being a. Let us make an interesting observation here. I'm going to ask the question, what happens if m1 equals m2? In other words, what happens if we make the two atoms, the red and the black atoms, equivalent? So this is an interesting question, and the answer is, of course, that we will recover the result of the previous lecture, meaning it is as though we have only one atom per basis. And in fact, that's the situation. If you make these two red and black atoms equivalent, then you recover the original picture. In fact, this observation is going to give us a clue to the solution for this new problem. And so before we actually go through the math and derive the actual result, we are actually going to preview the solution. Okay. So let's see what happens now. Let me make myself a little more room. So if we make the two atoms equivalent, m1 equals m2, and if we continue to assume that the lattice parameter now is a, we get the old result, which is what is pictured down below over here. See, this is a familiar result. Omega versus q has this behavior, and the limits of our q, or the unique q region, are plus pi over a and minus pi over a. Now we are going to look at the same case a little bit differently. Let's look at this lattice over here. If we now assume that the two atoms are equivalent, but the lattice parameter is 2a instead of a, meaning we have a 1D lattice with lattice parameter 2a and two atoms per basis, these two atoms, and assume that the two atoms are the same. Physically, it is the same as this case, but how will our omega versus q look like? I'm just going to draw it and then we will discuss. So here is our same 1D lattice, but now we are saying that the lattice parameter is 2a, and we of course have two atoms per basis. So these two lattices are physically equivalent, but our definition of the lattice parameter is different, right? It's 2a instead of a. So now I've drawn the omega versus q diagram. Well, not quite. I just drew the axes, and as a preview, as a prelude to what we are going to get for the answer, I have drawn a couple of more q values. So in addition to the plus pi over a and minus pi over a, and I'm showing pi over 2a and minus pi over 2a. I'm going to pause for a moment to ask if you can guess why. The reason is that now our lattice parameter is 2a in real space, and so the reciprocal lattice vector corresponding to that has to be 2 pi over 2a, which is pi over a. So the Brillouin zone should extend from 0 to pi over a, or in other words, from minus pi over 2a to plus pi over 2a. Right? So the Brillouin zone for this case has to be half in size with respect to this case. right? Because the lattice parameter is A here, the lattice parameter is 2A here. So the real space lattice parameter is 2 times as big, so the reciprocal space size, the lattice vector, has to be half the size. And so the Broughton zone boundaries for this system is going to be pi over 2A to minus pi over 2A. So interestingly, here is how our omega versus q plot is going to look for this case. Note that this picture is physically equivalent to this picture, right? So what has actually happened is something called zone folding. Because for this definition of lattice parameter being 2A, our Broughton zone is restricted to be in this region, and so this piece of our original dispersion diagram has actually folded over, or it has actually been translated. This piece here has been translated to this piece, and this piece has been translated to this piece. So that's what is going on. So this is kind of what you would get if you were to define your lattice as something with a lattice parameter 2A. Now, here is a twist. We now assume that these two atoms, the red and the black atoms, are equivalent, and we ended up with this structure, with this solid. Now let us go back and say that, oh no, our red and the blue our black atoms will have to be switched to a red and a black atom, right? Then what happens? What happens is a gap will open up at these Broughton zone boundaries. And so now, instead of having one strand, omega versus q line, we are going to get this piece over here, just the way it is, but a gap opening up here. And so this piece is going to get moved upwards, or it's going to be displaced with respect to this piece. Okay, so I've just written down my observations. Zone folding is what has taken us from the left picture to the right picture, and now if we make M1 not equal to M2, a gap will open up at plus minus pi over 2A. So that's the new feature I was talking about earlier. Okay, let me make myself a little more space, and let's now get to the mathematics behind all of these observations. So here are two equations that should look somewhat familiar. They are almost identical, analogous to the equation that we wrote down for the previous example of 1D lattice with one atom per basis, right? So this is Newton's equations of motion. Alpha is of course the force constant, and we are assuming that the force constant is the same for any pair of atoms. We are assuming that a given atom is directly interacting only with its immediate neighbors on either sides. And M1 and M2 are of course the masses of the two different types of atoms. So we are writing an equation of motion for each atom type, right? So that, which is why we have two equations here instead of just one, as we saw earlier in the previous lecture. So two equations, two differential equations, and so we are going to propose a solution that is really a pair of solutions. And we, just like before, we are going to propose a general solution. We are going to substitute that general solution, which would be the displacement of the at the two different atoms. So we're going to propose general solutions for U2n plus 1 and another similar solution for U2n plus 2, and we're going to plug that into the these two equations, and we're going to find something interesting. So here are our two general solutions, one for the atom at 2n plus 1 and the other one for the atom at 2n plus 2. And A1 and A2 are two amplitudes, and so these two solutions will be substituted in the two equations above. When we do that, when we substitute these two solutions into the two differential equations above, do the algebra just like we did it for the case, the simpler case in the previous lecture, we'll find that we'll get two equations. Those two equations can actually be written in matrix form, and that's what you see in blue font, blue lettering over here. So the two equations that we end up with can be written in this matrix form essentially. So we are going to call this equation as equation A for later use. And of course, we know that if we want this set of two equations to have a non-trivial solution, meaning a solution where A1 is not equal to 0 and A2 is not equal to 0, then the determinant of the square matrix has to be equal to 0. Let's write that down. So there it is, that's our determinant of the square matrix, and that determinant has to equal to 0 if we want to be guaranteed that a non-trivial solution exists. Now, this determinant can be evaluated, and once you evaluate this determinant, you can solve for omega. Remember, our goal is to get a omega versus q relationship. So, we evaluate the determinant of this, we evaluate this determinant and solve for omega. So here is what we get. Essentially, this determinant leads to a quadratic equation, and then you solve for the omega with this quadratic equation. You get this relationship, this equation, this answer for omega squared, right? So now what we can do is we can try to plot omega as a function of q. This looks like a cumbersome equation, but the limiting cases can be quite easily understood, right? So let's go ahead and do that. Let me make myself a little more room over here so I can plot the omega versus q behavior. So here it is. So if you were to, for example, use Excel to plot omega versus q by taking suitable values for m1, m2 and alpha and a, you would get a plot like this. Bear in mind that the upper and lower limits of q that we have chosen here are minus pi over 2a and plus pi over 2a. These are the Brevon zone boundaries for our chosen lattice, which has a lattice parameter in real space of 2a. And you will see that if you were to plot this relationship yourself, that you would see a periodicity with periodic length along the q-axis of pi over a. So this pattern that you see will keep repeating essentially to the left and to the right, right? And as I had observed earlier, you see a gap. You see that a gap has opened up at the Brevon zone boundaries, and that's what you would see. Now we are going to try to evaluate what are the limiting values. What is this? Of course, this is 0. We know that. What is this value? What are these values, right? And what is the value of the gap? And that's kind of almost trivial. First, let us set q equals 0, right? So we are trying to find out what values omega can take when q equals 0. So when q equals 0, of course, we know from this plot that omega equals 0 is one solution and omega is something else. Non-zero quantity is another solution. So if we go back to our equation over here and set q equals 0, right? So this term drops out, and then you have a square root of a square, right? So it's alpha times square root of that, which is 1 over m1 plus 1 over m2. That's exactly what you got here, alpha times 1 over m1 plus 1 over m2. You got plus minus sign indicating that there are two solutions, right? If you chose the minus sign, this quantity is going to cancel that quantity, so you get 0, that is this solution. If you took the plus sign, then you get 2 times alpha. The solution would be 2 times alpha times 1 over m1 plus 1 over m2, the square root of the whole thing, right? Because this is omega squared, remember. So to get omega, you need to take the square root of whatever is on the right hand side. So that's what this is. I've written this down here. So the upper solution is a non-zero quantity, and it's equal to this. Now the next step is to evaluate what these numbers are, right? So to do that, it's a simple matter. We take pi over 2a and substitute it in here. So q we set q equals pi over 2a, and then we see what we get. So when we do that, we get this interesting result, right? So when you set q equals pi over 2a, again you get two solutions, and one of them is 2 alpha over m2 square root, and the other solution is square root of 2 alpha over m1. So the only difference between these two is that the two different masses show up. So those are these two values of omega, and of course the gap is going to be, the gap that has opened up is going to be equal to the difference between these two quantities. Now note that if m1 equals m2, and this is something we had considered a little earlier. If m1 equals m2, these two quantities will be the same, and so this gap will vanish. So an important outcome of this exercise is that now our omega versus q relationship behavior, the line that described the omega versus q relationship was a single line earlier. Now it has broken up into two pieces. Right? It has broken up into this piece over here, which is a single connected line, and then there is a second piece over there, which is that. Now these two strands, these two branches, they have their own name. This lower one is called the acoustic branch, and the upper one over here is called the optical branch. Now, why are these two branches called acoustic and optical? Right? In order to understand that, we need to consider the long wavelength limit. We need to visualize the pattern of vibration of the atoms in our lattice. So the names actually have their origins in the nature of the patterns of vibration, essentially. So we are going to try to do that. Let me again make myself a little more room. So here are some thoughts. So we would like to understand the meaning of the acoustic and the optical nomenclature. In order to do that, we need to consider the long wavelength limit, right? The q tending to 0 limit, and we need to determine the pattern of vibration of the acoustic and the optic branches, the modes contained in the acoustic and optical branches. In other words, we need to determine A1 and A2. Right? Remember, A1 and A2 are the amplitudes of oscillation. So determining A1 and A2 for certain limiting cases will allow us to picture how the atoms are actually moving. Right? So what we will do is, remember we defined equation A earlier on. So we are going to go back to that equation A. We are going to set q equals 0 because we want to visualize the long wavelength limit. We are going to set q to 0 in that equation A, and then we are going to set omega to the appropriate values for the optical and the acoustic branches. So we'll do the acoustic branch first. Okay, so what we're going to do is we're going to go back to our equation A. We're going to set q equals 0 because we want to look at the long wavelength limit. And in addition, we're going to set omega to 0 because we are interested in the acoustic branch first. And if you go back to this plot over here, we are interested in the acoustic branch, and when q tends to 0, the acoustic branch, you would get the acoustic branch when omega is also equal to 0. On the other hand, if you want to look at the optical branch at q equals 0, you need to set omega to that value, right? So we're going to go back to our equation A, set q equals 0 and set omega equals 0 as well, and then we're going to ask the question as to what the values of A1 and A2 would be, right? So okay, so here is our equation A that we had originally set up. So we're going to set q equals 0, right? Q equals 0, so these two terms become 1. And then we're going to set omega to 0 as well. When you do that, when you write down, expand out this matrix equation, you will find that the two equations that you get can be right only if A1 is equal to A2, right? So which is why we wrote down this equation over here. So for the acoustic branch, setting omega equals 0 in equation A, that particular equation will be satisfied only if A1 equals A2. Likewise, we are going to go back to our equation A. Now we want to understand the optical branch. So we are going to set, in addition to Q tending to 0, we are going to set omega equal to this particular value. We already know what that is. We are going to set that in our equation A, which again let me show you, it's over here. We are going to still set Q equals 0. And in addition, we are going to set omega to the appropriate value for the optical branch, and then we are going to evaluate the expression, the relationship between A1 and A2. So we're going to find something different, something interesting for the optical branch. Okay, so this is what we get for the optical branch. You see, so as Q tends to 0, when you set omega to 0, we are talking about the acoustic branch. We require that A1 equals A2. On the other hand, if for Q equals 0, you set omega equals this quantity in the square root of 2 alpha times 1 over m1 plus 1 over m2, then we get the equation that I just wrote down, which is m1a1 plus m2a2. I'm sorry, that should be m2a2 should be equal to 0. Now, if you assume that m1 and m2 are the same, then you can see that this equation implies that a1 has to be negative a2. So this means that if for the acoustic branch you want a1 equals a2, and for optical branch it implies that a1 is negative of a2, it basically means that in the case of the acoustic branch, both types of atoms are moving in the same direction, and in the optical branch, the two different types of atoms are moving in opposite directions. Let's just let me just write this down. Let me just create a couple of quick pictures. So this is what is going on. So in the case of the acoustic branch, you see that both atoms are moving along the same direction. The arrows indicate that they are going along the same direction, and in the case of the optical branch, they are opposed to each other. Of course, at as Q tends to 0, the real long wavelength limit, we expect A1 equal to A2, but for Q very close to 0 but not quite 0, the two arrows, the two values of A1 and A2 need not be exactly the same. And so there is some kind of a modulation. But the point is, the displacements are along the same direction in the case of the acoustic mode, and the displacements are opposed to each other for the two different types of atoms for the optical mode. So what, right? I mean, the point is that when the two atoms are moving along, when these atoms are all moving along the same direction, the net dipole moment is not going to be changed. Remember that we have two different types of atoms with masses m1 and m2. They probably have different electronegativities as well, which means that when atoms move around, the dipole moment in the system could be changing. But if all atoms are roughly moving along the same direction, the net dipole of the system is not going to be changing that much. On the other hand, if the two unlike atoms are moving along opposite directions, then the net dipole moment for this unit over here is actually changing quite drastically during the course of this vibration. If the dipole moment is actually oscillating quite violently, it basically means that this type of a vibrational pattern can be excited by an electromagnetic wave. And that is the reason this type of mode is called the optical mode. So there it is. Here is the reason why the top branch is called the optical branch. It can really be excited by electromagnetic waves or optical waves, and hence the name. So now we are actually going to very smoothly and quickly move on to higher dimensions. We are going to move on to three-dimensional systems, and we are going to just make some important observations with respect to that case. So in 3D cases, there is one major difference with respect to what we have seen earlier. Although we should say that most of the arguments that we have seen before smoothly carries over to 3D situations as well. As I said, except for one major difference. In the case of 3D, the displacement of atoms can be in three independent directions. So three independent directions, one of which can be along the wave propagation direction, and that is called as the longitudinal direction or the longitudinal mode, and you can have the other two perpendicular to the wave propagation direction, which are called the transverse directions. Of course, bear in mind that your displacement u is now a vector, the amplitude a is a vector, and the q, the wave number which we have been talking about all along, which had been a scalar, now is actually also a three-dimensional vector. So so in that sense, the solution that we used earlier is going to just get generalized. So there it is, the u vector equals the a vector times e to the I q dot r minus omega t. And for longitudinal waves, the amplitude a vector is parallel to the q vector. So a represents the unit vector a really gives you the direction of oscillation of your atoms, and the direction corresponding to the q vector gives you the wave propagation direction, which is actually why it's called the wave vector. Right? On the other hand, for transverse waves, the a vector is perpendicular to the q vector. And also we should note that for a 3D monatomic crystal, we discussed 1D monatomic crystal. Now if you have a 3D monatomic crystal, in general we'll have three branches. So here is a picture of what you can expect for a 3D monatomic crystal, by which of course we mean that we have a 3D lattice and we have one atom per lattice point, right? Which is why we call it the monatomic crystal. So for a 3D monatomic crystal in general, we will have three distinct branches. Although I should point out that along certain high symmetry directions, remember Q is a vector. So what I'm showing here is really just a schematic. So Q is really a three-dimensional quantity, and along certain high symmetry directions, two of the transverse branches could be degenerate, meaning they can lie on top of each other. So there you have learned a new technical word, degenerate. Degenerate in this context basically means that either the energy is the same or the frequencies are the same of two different modes. So two states are said to be degenerate if they have the same energy or the same frequency. Okay, so now let us ask a general question. So we said that for a 3D monatomic crystal, we will have three distinct branches in general, right? Supposing it's not a monatomic crystal, it's a 3D lattice and you have more than one atom per basis, right? So the question is, how many branches will you have? In fact, how many optical branches and how many acoustic branches? Actually, before we even address that question, let's get back to the same picture that we are looking at right now. Note that there are only acoustic branches in this case, no optical branches. So whenever you have a monatomic crystal, be it 1D, 2D or 3D, you can have only acoustic branches. There will be no optical branches. On the other hand, the moment you have more than one atom per basis, you could in principle have acoustic and optical branches. In fact, your guaranteed to have both types of branches if the number of atoms per basis is more than one and they are of different type, right? So the question now is, let's say you have R atoms per lattice point, per unit cell, per primitive cell. So you have R atoms per primitive cell and it's a 3D situation. So the question is, how many branches will you have? I'm going to give a moment for you to think about it while I write down the answer. So there is the answer. In a 3D crystal with R atoms per lattice point or per primitive unit cell, you will have 3 acoustic branches and 3R minus 3 optical branches. So if R is a big number, you are going to have plenty of optical branches. But note that the total number of branches is of course 3R, right? 3 plus 3R minus 3, that's going to be 3R. So the total number of branches is going to be 3R. For each branch, of course, note that you will have n modes, right? N possible Q points if there are n unit cells. If there are n primitive cells, then each branch will contain a total of n allowed Q values. Okay, so here are our thoughts on this matter. 3D crystal with R atoms per primitive unit cell contains 3 acoustic branches, 3R minus 3 optical branches, which means a total of 3R branches. There are n allowed Q points per branch, so total number of modes is 3Rn. And you can make sure it all makes sense also by looking at the total number of atoms in our system. If there are n unit cells, there are nr atoms. Because it's 3D, there are 3nr degrees of freedom. So 3nr degrees of freedom, 3nr modes in our dispersion diagram. So it all makes sense. In the last minute or so of this lecture, we are going to go back to our concept of density of states, and we are going to actually close the loop on something quite important. So here is the formula that we have used, we have seen before for a one-dimensional solid in the continuum limit, right? Within the continuum picture, we are going to get a value for the density of states which was a constant for in the 1D situation. So G of omega is our density of states. It's equal to L over pi 1 over d omega dq, and which works out to be a constant quantity for a continuum solid. The question is, when we put the atoms in for a discrete solid, whether the density of states will be a constant even for a 1D situation. It turns out that it is not a constant, and let's see what the answer is. So this is the answer for a discrete solid, and you can go back to the omega versus q relation that we had derived in the last lecture for the 1D monatomic lattice, and then you can stick it into this equation up top, and then you will get a relationship g of omega, which is actually not a constant. So if we now plotted G of omega, G versus omega for the continuum versus discrete solid, here is what we are going to see. So there we go. So here is our plot, our density of states plot as a function of frequency, and the horizontal straight line is the continuum result, which is a constant, right? So the discrete result actually is the same as the continuum result for very small values of omega, but as you go to higher values of omega, it deviates from the constant result. And of course there is the upper cutoff, which is omega m. So we don't have any density of states above that omega m. What about in the 3D case? Let's very briefly take a look at that. So here is the picture for the density of states for a three-dimensional solid. We have three curves in here. One of them in black is the Dubai picture, where the density of states varies quadratically with respect to omega. And there is a delta function in red, that is the Einstein assumption. And of course, the blue line is the actual result when atoms are explicitly taken into account and full quantum mechanical solution is sought. So as you can see, the Dubai picture is not really that far off, which is one of the reasons the predictions of the Dubai model for the specific heat of solids was incredibly accurate. But of course, if you use the discrete picture and solve the problem using quantum mechanics, then the result that you get is an even better agreement with experiments. It becomes near exact. On that note, I would like to share with you one final thought, and this has to do with what we really mean by phonons. We first started off this entire set of discussions by considering a continuum solid. We disregarded the presence of atoms. We considered the vibrations coursing through this continuum solid. And then we decided not to disregard the atoms. We put the atoms back in, and that took us to discrete solids. Now, for this discrete solid, we once again solved Newton's equations of motion for the motion of each of the atoms, and we got our solution. If we have n atoms in our solid, a total of n atoms in our discrete solid, we will have 3n degrees of freedom, which means that we will have 3n modes of vibration with 3n possibly distinct frequencies. Now comes quantization. If we now allow each mode to have energies that's an integer multiple of h bar omega, where omega is the frequency of that mode, then we have introduced a quantum mechanical notion. We have introduced quantization of the energies of those oscillators. Those quantized lattice waves are what are called as phonons. So the discretization of the solid into atoms, identification of the modes of vibration corresponding to all the degrees of freedom, and quantization of the energies of those oscillators, of the lattice waves. All of that leads us to phonons. That's what constitutes phonons. That concludes this discussion. Thank you.